All right, this video is going to go over pages 24 through 26 in your working energy packet. So we have number 7, a man pulls with a string on a 20 kilogram mass. So there's your mass initially at rest. So that means your VI is 0 on the floor. He exerts a force of 20 newtons. So there's your force. Okay, horizontally, and the mass moves through 8 meters. So there's your distance. The mass then has a velocity of 3 meters per second. So that'd be your VF. Okay, what is the final kinetic energy? Okay, so remember, kinetic energy is 1/2 mv squared. Okay, so the initial kinetic energy would be 0 because you were at rest, so there is no initial kinetic energy. Okay, so the final kinetic energy, all we have to do is plug in our mass and our final velocity. That would be 1/2 your mass, which is 20, times your velocity. Let me fix that. Times your velocity, which is 3, and that's squared. Okay, don't forget the squared, and you get 90 joules. Okay, how much energy has been transferred from the man? Okay, so that was the final kinetic energy. So the man is applying work. So it says, note the energy transferred from the man equals the work that the man does. Okay, so remember, work equals force times distance. Okay, so the man pulls on that object with a force of 20 newtons, and it's for a distance of 8 meters. Okay, so what you would do is you multiply those, and you get 160 joules of work. Okay, now, typically what we have is it would be called conservation of energy. There's a discrepancy here because the man's putting in 160 joules of work, but there's only 90 joules of kinetic energy coming out in the end. Okay, so that means C, it says, how do you explain the difference in your answer between A and B? Okay, so in a perfect world where there isn't things like friction and stuff, okay, then we wouldn't have to worry about it. But if I'm applying 160 joules of work, so even if there's friction there, the man is still applying this much work. Nothing changes that. Okay, but when we look for things like terms like net work, like what are the total forces that are going on, okay, that means we lost energy somewhere because we put in 160 joules of work, but we're only getting 90 back. Okay, so what that means is we had to have lost it due to friction. So that means the work that friction is doing would be negative 70 joules. Okay, so your answer would just be you lost it due to friction. Okay, so when you see terms like net work, and then on the test, we would be very specific. Okay, so if you see terms like net work or net force and stuff, net means everything combined. Okay, so if I asked you what was your net work going on in this, it would actually be your 90 joules up here. Okay, because the man is putting in 160 joules of work, we're losing 70 joules due to friction, so the net work would be 90. Okay, so remember, net just means total. So the way I try to remember that is you cast a net and you try to catch everything. Okay, so that would be net work. Okay, number 8, compare the kinetic energies of two objects, A and B, identical in every respect except one. Because that means we're only changing one thing. Okay, because if you're talking about kinetic energy equals 1/2 mv squared. So if we change V, that means we're keeping mass the same. We're only trying to change one thing at a time. If you start changing both things, then it starts getting more complicated. So that's what that means. So we're keeping everything the same except for one thing. Okay, so A is object A has twice the velocity of object B. Okay, so when you look at this equation, KE equals 1/2 mv squared, if you increase the mass, okay, kinetic energy is going to do the exact same thing. Okay, so let's say I double the mass, my kinetic energy is going to double as well. It's just going to do the exact same thing. But when you look at velocity, velocity has this squared right here. Okay, so if you increase velocity, yeah, kinetic energy is going to increase. Okay, but that squared is going to make it go up exponentially. Okay, so if I increase this velocity by 2, okay, so we're doubling it, that means my kinetic energy is going to go up by 2 squared, which is going to be 4. So your kinetic energy is going to go up by 4. So that means the kinetic energy of object A is 4 times the kinetic energy of object B. Okay, so just be careful with that squared. Okay, if I were to triple that, like if I tripled the velocity, my kinetic energy would actually go up by a factor of 9. Okay, or if you go the opposite way, if I take my velocity and I go down by 1/2, okay, so let's just say we divide it by 2, okay, your kinetic energy is going to go down by divided by 2 squared, so it's going to be divided by 4. Okay, so just watch out for that squared. B, object A moves north, B moves south. Okay, so one's going this way, one's going this way. Okay, would there be a difference in kinetic energy? No. Okay, so that means the KEA equals KEB. So direction doesn't matter. Okay, the only thing that can affect kinetic energy is changing the mass or changing the velocity. So C, object A moves a circle, B moves in a straight line. Nope. Okay, so it's just direction. So in this case, kinetic energy is going to be the same for both cases. And the last one, object A is a projectile falling downward, and yet projectile B is moving vertically upward at the same speed. Key thing there is same speed. If they have the same speed, then they have the same kinetic energy. So KEA equals KEB. Okay, so the takeaway from there is direction doesn't matter. Direction is not going to change kinetic energy. But if you change mass or velocity, that will affect kinetic energy. All right, moving on to, we're doing a little bit of graph stuff. We have a 3 kilogram mass. Please don't forget to read these clues that were given with the problem. Accelerates from rest, so your VI is 0. So you have your mass right here. Okay, so determine the kinetic energy of the object at all these times. So if you look at your axes, you got force and distance. We know work equals force times distance, but we also know work equals kinetic energy. Okay, so if I ask you to find the work on a graph, find the area. If I ask you to find the kinetic energy on a graph, find the area. Okay, so we're just going to find our things here. So up to 2 meters. Okay, so we're going to figure out how much kinetic energy we have up to 2 meters. Okay, so don't forget your triangle is 1/2 base times height. So your base is 2, your height is 3. 2 times 3 is 6. Half that is going to be 3. Okay, so you're going to get 3 joules of kinetic energy just by doing the area of a triangle. Okay, so at 6 meters, that means we got to add it all up until 6 meters. Okay, so now we got a square. So this little triangle is 3. Okay, so we have our base is 4, our height is 3. So that means our little square right here is 12 joules. So add all that up, and you get 15 joules at 6 meters. At 11 meters, okay, so 11 meters is going to go down here. So we got to add up some more. Okay, my base will be from 6 to 11. That's 5. 5 times 3 is 15. Okay, add all that up, and you get 30 joules of kinetic energy. Now, at 14, okay, so we have another triangle here. So our base is going to be 3. 3 times 3 is 9. Half that is going to be 4.5. We were so close to having no decimals. Oh, well. Okay, so add that all up, and that means our total kinetic energy will be 34.5 joules. Now, it says, what is the final velocity at 14 meters? Okay, so remember, kinetic energy equals 1/2 mv squared. Okay, or it could be at 1/2 mvf squared minus 1/2 mvi squared. Now, in this case, vi is 0, so this whole thing goes away. That's just 0. Okay, but if there were initial velocity there, you would plug it in right here, and that means you're looking for what is this final velocity right there. Okay, so your kinetic energy you already know. Okay, you found that was 34.5 equals 1/2. Your mass, we told you at the top, that was 3 kilograms. And velocity, we don't know. We're going to leave it as v, and that is v squared. Okay, so divide both sides by 1.5 to clear up that 1/2 times 3. And then don't forget to take a square root of your final answer to get rid of that squared, and you get a final velocity of 4.8 meters per second. Okay, number 10, a person strikes a nail with a 0.75 kilogram hammer. There's your mass. Moving at 10 meters per second, there's your VI. And drives the nail 1.5 centimeters into the piece of wood. Okay, so that is distance, but we're going to go ahead and fix that. So divide by 100. Okay, so that's going to give you 0.015 meters. Okay, so make sure you're in meters. Now it says, what is the kinetic energy of the hammer? Okay, so we want to know what is the kinetic energy of the hammer as it comes down to hit that nail. So KE equals 1/2 your mass, which is going to be 0.75. Okay, and then your velocity is 10, and that's squared. And you get a kinetic energy of 37.5 joules. Okay, what was the average force opposing the motion of the nail? So that means that nail had to come to a stop. Okay, only went 1.5 centimeters into the wood. Okay, so remember we said this big equation right here, work equals force times distance, which also equals change in kinetic energy. Okay, so we can say F times D equals 1/2 mv final squared. Oops, let me fix that. mv final squared minus 1/2 mv initial squared. Okay, so if you're coming to a stop, that means this whole final kinetic energy goes to 0. Okay, so what force? We're looking for force. Your distance is 0.015. Okay, your final kinetic energy is 0, so you can't just get rid of everything. It's still 0 minus 1/2 your mass, which is 0.75. Your VI is 10 squared. Okay, so all you're doing is you're solving for F here, and it's okay to get a negative force because it's opposing your motion, and you should get a force, stopping force of negative 2,500 newtons. Okay, moving on to the next one, we have how does the kinetic energy of a car change when the speed is doubled? Okay, so we just talked about that. So KE equals 1/2 mv squared. Okay, if we take this velocity right here and we go up by 2, okay, our kinetic energy is going to go up as well, but it's going to go up by a factor of 2 squared, which is 4. Okay, so just don't forget that. 2 bodies are of unequal mass. Each have the same kinetic energy, so key thing there. So they have different sizes, but they have the same kinetic energy, are moving in the same direction. If the stopping force is applied to each, or same stopping force is applied to each, how will the stopping distances of the bodies compare? Okay, if they have the same kinetic energy, okay, so same kinetic energy, that means stopping distance will be the same as well. So stopping distance is the same. So even though they have different masses, they both have the same energy. So in that case, mass doesn't even really matter if they have the same energy. Now, if you started saying one has a bigger mass and has more kinetic energy, then it would probably take more to stop that object, which would make their distance longer to stop. But key takeaway there is if they have the same kinetic energy, it's going to take the same force to stop them and same distance to come to a stop. 13, how is it possible to exert a force and yet not cause a change in kinetic energy? Okay, so key thing here is change in kinetic energy means you had to change in your speed. Okay, you either had to go to a stop, okay, you had to come to a stop, or you had to speed up. Okay, so there's a couple of things here is if there's no distance covered, okay, so the object doesn't even move, so one would be object doesn't move. You can still, like I talk about this, is when you push on a wall, that wall is not going to go anywhere. Okay, so that doesn't stop you from applying a force. Okay, but you're not technically doing any work because you're not making the object move and you're not making it speed up, so there is no change in kinetic energy. Okay, also, if you have things like circular motion, okay, when your force and your distance are and your distance are perpendicular, okay, then there would be no change in kinetic energy there. Okay, so you're looking for you're looking for scenarios where most common one would be applying a force to something and it either doesn't speed up or slow down, okay, or it just doesn't even move at all. Okay, so that was your big takeaway from that one. 14 is a bullet of mass 12 grams. Okay, so we're going to go ahead and fix that. Okay, can't have grams, so divide that by 1,000. Okay, so that's going to be 0.012 kilograms. Okay, strikes a stationary block of wood at a speed of 400 meters per second. So there's your VI. Okay, penetrating to a depth of 3 centimeters. So let's go ahead and fix that. Divide by 100, and you get 0.03 meters. Calculate the average net force. Okay, so just because you see net force here, so you're still just looking for force. So force is your question mark here. Okay, acting on the bullet while it's in the wood. Calculate the average force exerted on the wood by the bullet. Okay, so basically we're just looking for the stopping force of that wood. Okay, so remember we said F times D equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, so if it comes to a stop, that means this final kinetic energy is 0. Okay, your force we don't know. Distance is 0.03 equals 0 minus 1/2 your mass, which is 0.012. Your VI is 400, and that is squared. And if we do our math correctly, you should get a stopping force of negative 32,000 newtons. And that'll end that one.